Hi everyone, my name is Tony and today I'll be presenting to you about my project on the Tahoe Basin snow coverage. So now for a little bit of background. Snow coverage is obviously an important thing to understand for many reasons. For one, it plays an important role in hydrology, which in California is especially important, and also has a significant effect on wildlife habitats. But for me personally, I chose this topic because I really like skiing, and Tahoe is where I do most of my skiing. So it has, a place in my heart. This project focuses on the Normalized Difference Snow Index, or NDSI, which I'll talk more about later. So first, where exactly is the Tahoe Basin? Well, the Tahoe Basin Study Area boundary is outlined by the Tahoe Regional Planning Agency, or TRPA, and you can see it here on the right in this map I provided. Basically, I downloaded the shape file from the TRPA and used it to clip my Landsat imagery. Now, location is one part of the equation, but the other part is time. So choosing the dates for the data was a very important part, especially with something like snow coverage because it changes throughout the year. So I decided to focus on February and March to gather my data from, because that's typically when there's peak snow coverage. Although, as you can see with these three maps, April is also a good month to use for something like this. But I kept it down to 2 months because for this data I used it over 10 years, and 10 years is a lot. That would be a lot of data to use, so I wanted to limit it by keeping it to only 2 months. So how did I determine snow coverage? Well, I used, like I said before, the normalized difference snow index, or NDSI, and this is actually a very simple calculation. It uses the bands 4 and 6 from Landsat 8, which are the green and shortwave infrared bands respectively. This calculation gives an index value ranging from -1 to 1, and values closer to 1 indicate a higher probability of snow presence. Now, how did I employ this NDSI in this project? Well, unfortunately, ArcGIS Pro doesn't really have a built-in NDSI tool, so I had to make my own using Python. On the right in this image, you can see the code I use. It's not very long, it's pretty simple actually, and I used some code provided by Esri in their ArcGIS Pro documentation, but I had to edit it and debug it for a while before I got it to work. And so this tool takes the original Landsat imagery as its input and calculates an NDSI value for each pixel of that image, and then outputs a raster layer that displays NDSI over that entire area. So what does this look like in ArcGIS Pro? Also, here's my original example imagery that I was using to test out my methods before I decided on the actual data I was going to use. On the left, you can see the Landsat imagery clipped to my boundary polygon. On the right, you can see the NDSI raster layer I generated using my script tool. It looks pretty good, but there are some problems with this method. So the two main problems I ran into using the NDSI method were that, for one, it can't differentiate between clouds and snow, and it also can't differentiate between water and snow. So here's an example of where water becomes a problem with this method. So on the right, you can see a map of an NDSI raster I created from using imagery from March 2016. And in the middle, you can see the water is all gray, which means that it has an NDSI value. And if you look at the NDSI distribution histogram I created on the left, the first thing you notice is a big spike in the data, which otherwise is a pretty smooth distribution. And so that can be a problem when analyzing this NDSI data. Now, on the other hand, the clouds are also a problem. In this example, you can see that it's almost completely covered with clouds, and you can't see the ground. You can't see the NDSI, the actual NDSI of the snow on the ground. And if you look at the distribution, it looks pretty normal but skewed, which at first might seem like a good thing, but because of this, it's actually pretty clear that the cloud coverage is much more difficult to deal with than water when calculating NDSI, because in the previous slide, as we see, the pretty normal distribution just showing the NDSI, but the big spike where the water is. But here it's all over the place. So what are some potential solutions for the water problem? Well, one solution is to just remove the large bodies of water from the raster. And there are many ways to do this, but one way that I would look into doing this is using a digital elevation model to find the flat areas in the map, which typically indicate a large body of water, and then using that to create a polygon or some feature that can be used to clip that water area out of the raster, and then you can use that just to calculate the NDSI on its own for just the areas where snow can be. But another method, potential method, is to just leave the water in there, calculate the NDSI, and then factor out the water's NDSI value out of the distribution. Because like I've been saying, it shows a pretty smooth distribution with just one spike in it. So if you can factor that spike out, maybe fit the data and project where that NDSI value would be if the water wasn't there, then maybe you can analyze it further. So now what are some potential solutions for the cloud problem? Well, like I said before, the cloud problem is a much more difficult problem to deal with than the water problem. And so essentially the most feasible solution is to only use imagery that has little to no cloud coverage. So it's a matter of properly choosing the data. So in conclusion, calculating NDSI is a great way to determine snow coverage, but it has major drawbacks when there is significant cloud coverage or significant water presence. So employing other methods is often necessary to ensure that the NDSI calculations are accurate. Thank you for listening to my presentation.